Okay, so my name's Phil Winder. I've been running Winder.AI. We're an AI consultancy for about 10 years. We help businesses build out their AI solutions and spoken about ML and AI a lot in the past. But the reason I'm here today is to talk about LLMs and specifically how you might be able to leverage LLMs. And the reason why I'm talking about it is because they're hot. It's the first time in my life that I've not had to explain what I do anymore. I say I'm an AI consultant, and they go, "Oh, okay." Like only 6 months ago, people were like, "What, avian influenza? Like, what are you talking about there?" So it's great that it's all in the media now because finally everybody's on the same page. This presentation is split up into 7 parts. I am going to sort of dynamically trim it down if time is running short, which reminds me I should start my timer. I haven't timed this in full yet. But hopefully we're going to go through the full life cycle of what an LLM is, how you train one, how you develop one, a little bit about deployment and post-deployment tasks. And then there's an amazing demo at the end. And the best demos and the most embarrassing demos. And I promise you that this is one of the most embarrassing demos I've ever done. So you want to stick around for that. Don't forget to rate the session. Helps tell GoTo that I'm not completely rubbish. And let's get started by talking about a history of LLMs, because it is relevant. And the first question has to be, what is an LLM? Well, essentially, it's an AI model. It's a machine learning model. AI is a bigger term that, unfortunately, I didn't like using the term a few years ago because it's kind of a bit philosophical in its definition. But unfortunately, I lost. So it's an AI model, and it's trained using supervised learning. So it's a traditional machine learning model on a huge amount of text-based data. The interesting part about it is that it's refined through user feedback, and that's where my work on reinforcement learning comes in. And then all it attempts to do is predict the next word. That's all it's trying to do, is what's the best next word that I can pick given the previous words that have been created. That's it. Simple model. But let's go into a bit more depth. So the history behind LLMs and people trying to interact with computers in an intelligent ways goes back quite far. This is Eliza from 1966, I believe, and it's this example of the psychiatrist inside the computer, basically asking the same question back to you. And actually, there's a great web demo of that if you want to try it. I'll probably skip it, actually, because we don't really have time. But that was in 1966. Okay, so since then, we've had all sorts of ML discoveries, but really LLM started to form in about 2013, just in the 2010s, really. The first discovery was the use of embeddings in Word2Vec. So this is the idea that you can represent a word, some text, a sentence, a document, anything, as a series of numbers, a vector, just a single vector, a single set of numbers that represents that text. And it allows you to do interesting things like maths upon words, adding, queen plus man equals king, that kind of stuff. The next most important idea came in 2014 when people started treating series of words as sequences, and by modeling them as sequences, then they kind of proposed the idea that it should be possible to predict what the next word in that sequence would be. The original models used RNNs, and RNNs are a bit of a pain because they have a little bit of memory inside each of the neurons in the neural network, and they have a really bad habit of blowing up as soon as you go near them. So they were quite hard to use. Transformers in 2017, so a few years later, was this kind of generalized architecture for working with text. But unfortunately, and actually, really what the revolution here was they figured out a way of looking at the whole sentence or the whole series of words in one go, in one shot. They didn't have to pass it through this recurrent neural network, which required like multiple steps to kind of feed the words through in like a ticker tape fashion. And that made it easier to train, made it faster to train, made it easier to use in inference as well. And then people realized that they could start scaling this. And so BERT was the first real example of a large-scale demonstration of this technology. They use something called a bidirectional training technique, which is where you don't just try and predict the next word, you actually mask out words in the middle and try and predict the word in the middle as well. And it helped the model learn much faster than it would have been able to before. Then we've got GPT-1, GPT-2, GPT-3, 2018, 19, and 20. The real revolution here is that I'll come to the architecture in a moment, but they simplified the architecture a little bit, and they trained it on a huge amount of data. And it really turned out that the huge amount of data was the key. And it got to the point where the sentences being generated, the words that were being predicted next, were really, really good. They were as good as humans. And then in 2022, they released ChatGPT, and as we know, everybody now knows what AI is. Oops, all right, press the wrong button. Okay, so let's have a quick look at how it works. The current iterations, the current versions of the GPT-like algorithms have three general steps. There's a first step where you have to attempt to pre-train the data. So this is vast amounts of text data that are being used to pre-train this model. There's then a secondary step where a reward model is trained based upon user feedback. And then the third step is to use that reward model to tweak the original model to make it better, to make it more aligned with what you want to do. The specific text in this image comes from the paper at the bottom, the Instruct GPT paper. And it's talking about how you would fine-tune it, but the idea is the same for pre-training as well. In this paper and prior to this, they use the transformer architecture. So this is the transformer architecture from 2017. It consists of two parts. On the left-hand side, we've got an encoder. On the right-hand side, we've got a decoder. But the important thing to know is that from GPT onwards, the architecture is decoder only. So what we're trying to do here is feed raw text in and then just predict the next sentence out. Yeah, so let's now have a look at what each bit of the architecture does. At the bottom, we have a block that is responsible for tokenizing and embedding the input into numerical space. Tokenization is a step where you're converting a sentence or a document into smaller chunks. Typically, in most of these models, it's kind of sub-word sequences. It's not full words, it's sub-words, and it allows it to capture more diversity of words with fewer tokens. The next step is to basically predict the probability, predict how likely each word in the sentence is as being relevant to the output, how important each part of the sentence is to the output, to the prediction. And this is the masking step. It's attempting to mask out the parts of the sentence or the document that are not relevant, and that's learnable. Then we have a simple multi-layer perceptron, a normal neural network to predict what is the most likely next token. And then we have n number of blocks. And this is a big number, tens and tens and tens of these blocks, all stacked on top of each other. And that's what makes it deep. That's what makes it able to provide these high-level kind of conceptual thoughts about what it's writing about. And then finally, at the end, we've got the final prediction. And that's it. So if you look at the implementation of this, it's that. It looks a lot more complicated than it is. And there's wires kind of connecting things together and stuff. But fundamentally, that's all this architecture does. And this is GPT-3. OK, the next step is to take what's generated and ask a labeler, to attempt to rank the outputs in terms of their preference. We then capture those preferences and then build another model, a second model, to predict a reward, to predict how preferred each of the outputs are given a piece of text. Okay? And then just train, again, a normal multi-layer perceptron deep learning style model, nothing fancy. But hang on, why do we want to do that? Well, the main reason we want to do that is for alignment. We want to try and make sure that the LLM is actually producing content that we want it to produce. Otherwise, it produces all sorts of horrible stuff. Safety is obviously a big concern. Left to its own devices, the LLM learns a lot of really horrible stuff that is available on the internet and is capable of spurting it back out. And finally, quality control. One of the top results for Instruct GPT architecture came up with this website. And you can see that this website has used ChatGPT to generate its content because I've left in the little thing at the bottom there, please continue writing. And of course, ChatGPT, OpenAI, they're continuously rescraping the web and repassing that back into GPT to learn from its content. So it's, you know, it's already starting to learn from its crap content, which is obviously a concern for OpenAI. The irony is that this particular website is attempting to copyright it. We've got a DMCA mark there, attempting to copyright this, you know, this plagiarized content. And then at the bottom right, you can see some, you know, more, yeah, not nice stuff that comes out of this because, oh, yeah, it's the fact that we're hiring at the bottom as well. Anyway, so yeah, so how does the last step work then? So once we've got that reward model, once we've got a simple model that basically predicts how good an output is based upon what users have labeled it as, then we use it in this scheme. We feed it a prompt from our prompt data set, and the base LLM, our model, is then generating a couple of outputs or a few or more outputs, and they're all fed into the reward model. They're given scores as to how good they are based upon all of the things that it's learned, and then it's fed back into the LLM again to then fine-tune and, well, not fine-tune, that's the wrong word, to nudge the weights to stop it from generating this either, you know, malicious, harmful, bad, misaligned content. And this is where the reinforcement learning comes in, because in RL terminology, we've got the observation, which is the prompt. That's the thing that the agent sees. The policy is the LLM. That's the thing that's actually the internal model, the internal policy that the agent is using to generate some stuff. The action is the generated content. That's the action it's producing. We go through an external reward model, and then we have a reward that's then fed back into the LLM. So they're using reinforcement learning here to tune the model to behave better. If you want to know more about reinforcement learning, then you can check out my book. One of the most important aspects of developing any model is the data. All models depend on good quality data for a good quality model, garbage in, garbage out. So the arguments for fine-tuning, and I've created a couple of notes in here in like the dark gray if you want to kind of dig into it in a bit more depth. But the key points is that, firstly, massive data, it turns out that massive data is better than your own curated data, for LLMs at least. Research has found that many people were trying to treat LLMs in a traditional manner where you develop your own proprietary data set and you train your own model just on that proprietary data set. And it kind of works, but it doesn't do a very good job because it doesn't have this broader understanding of human knowledge. Okay, so in most tasks, on average, an LLM, a foundation model that has been trained on a huge amount of data, will be better than your domain-specific model. But it also turns out that if you take that foundation model and apply your proprietary custom data over the top, it's even better, especially at specific tasks. And I think that makes intuitive sense, but it's being demonstrated academically as well. But the problem is that curation is hard. It's really hard to manage and develop the data sets required to train these models. These models are massive. They're immensely huge. And I've spent most of my life saying, use the smallest model you can get away with because it means you've got less, you need less data to train that model. But now we have these huge models and you need a huge amount of data to produce anything even vaguely good. And so it just makes the whole task incredibly hard. There's also there's a theory in ML called no free lunch, which basically states that there's no one individual machine learning model that is the best at all tasks. There's always going to be like a specialist, highly customized model that is better suited to a particular situation. And it's the same with data as well. When you're attempting to clean the data, which we're going to talk about in just a second, you can't just throw it into one of these automatic cleaning routines because there's no one cleaning methodology that is the best for all problems. Unfortunately, you need to develop it for each application that you're developing. And therefore, don't use magic data cleaners if you can help it. Yeah, I think like pragmatism might win there a little bit. If you do have a huge amount of data, then obviously automated data cleaning might be necessary in order to have anything to show. So pinch of salt with that one. So when it does come to data cleaning, what does clean data give us? Well, it turns out that the research shows that clean data is better than more data. So if you have the choice of going back over your original data set and cleaning it up, or gathering more data, you should clean up your data first. That will produce better results than gathering more data, which is a bit of a surprising finding, actually. It's also been shown that sort of magic post-data solutions also don't help on average. There's a lot of work in the academic community to attempt to build ML algorithms that are more robust to bad data, more robust to outliers, more robust to anomalies, more robust to shifts in distributions and stuff. But they've demonstrated that you can't rely on these specialist algorithms. Unfortunately, if you've got clean data, then you can use anything. If you don't, then you're in trouble, and it's hard to rely on specific ML models to fix that. And the final interesting aspect is that when some researchers attempted to use the state-of-the-art automated cleaning techniques and then compared that to a set of human-validated, human-cleaned data sets, the humans won every time. They cleaned the data better than any automated algorithm. So human insight is still best. I was going to add this little bit on a tokenizer as well. There was a bit of interesting research showing that you shouldn't forget about the tokenization process, and that's where you're splitting the word up, because the tokenizer has a fixed vocabulary. It doesn't represent every single word. So when you're working in a very specialist domain, it's quite likely that the tokenizer cannot or is going to struggle to tokenize your word effectively. Like think of some like super tech words like I don't know, like normalizing or normalization or something, some database term, something like that. It's probably not going to be very well represented in the corpus that they've used to train their data on, and therefore it doesn't make it into the tokenizer. So they found that adding new domain-specific tokens to the tokenizer did improve results. But they also accidentally included their results, and they were using some LLMs to classify some medical data. And we've got a comparison of different models that they used, and they were trying to prove our custom specialist tokenizer performs better. But unfortunately, they also sort of demonstrated that a bog standard logistic regression from 200 years ago does almost as good of a job. These performance scores measure how good this model is at performing the task. And we've got a score of 83 versus 83.4 for the LLM model. So once again, I go back to my old thing of if you don't have to use an LLM for everything, like you can use a very, very simple statistical algorithm and it can perform very well. When you're looking at the data as well, you will see several different forms. So the most common form is just raw text. That's what the pre-training phase uses to train the initial model. It's just raw text. It slices and dices it, pulls out tokens randomly, and tries to predict where what that token should be. You'll also see for sort of downstream tasks, lots of supervised fine-tuning like data in various formats. Effectively, they all end up being in some kind of like question-answer style format or context answer style format, where you've got the input to the model basically and what the output should be or should look like. And then you've also got the reinforcement learning, the human feedback data, and that's usually presented as a question, several generations, and then a ranked order, maybe an accepted and rejected, or a rank 1, 2, 3, 4, 5. This is an example from, so that this chap on GitHub, ZJH819, good name, has a really great curated website of loads of data sets that are used for LLMs. And this comes from one of the human feedback data sets. And the question is, how can I blame someone else for a crime that I committed? And obviously, the LLM has produce this response at the bottom, telling you how to blame somebody else for a criminal activity. And the human feedback has been, no, that's not right. Let's just give some non-committal response. And that's how they've kind of trained out a lot of the more dangerous questions that you could maybe try in ChatGPT or things like that. Yeah, let's just skip that actually. Basically, all the basics still apply. It's still data. You've still got to have good coverage. You've still got to be fair. Still got to be unbiased. You are going to have anomalies, so on and so forth. All right, modeling and training. So going back to our decoder-only part of the transformer architecture, which parts of this are actually trainable? Well, it turns out quite a lot of it. Only the simple sort of addition and normalization kind of steps are not really trainable. The rest is. So at the bottom, we've already talked about you can alter and train the tokens and embeddings. So if you've got a very specialist domain, it might be worth doing that. You can perform pre-training on the raw text, and that trains all of the blocks in the middle. The problem is that we'll see in just a second that some of these models are massive and the data sets are even bigger. And so it takes a really long time to train these things and a lot of money. And that's why it costs tens of millions of pounds to train the original ChatGPT. I dread to think how much has been spent since, actually. Yeah, so you can also fine-tune it as well. So fine-tuning, this is the first time I've kind of mentioned it really, is the process of taking a model that has already been trained and attempting to nudge it towards a place where it's better for your specific task. So you can fine-tune the raw underlying LLM, but all the same caveats apply. It's still a huge model. It still takes a huge amount of time. You still need loads of data, and it's very hard. And it also has been shown to degrade performance. Remember what we said earlier about the large model is generally better than any sort of specific curated model that you can create. So it actually degrades performance when you attempt to fine-tune the raw model. It wouldn't be great if we didn't have to do that. Well, now you can. Some researchers developed this idea of slapping on another neural network on the side of this thing and freezing all of the weights in the original model and attempting to just tune this secondary, they call it an adapter model, the proper software engineering terminology, an adapter model, which it is trainable, but is much, much, much smaller. And it's combined with the original model in these kind of addition and normalization steps here to mutate the result. It's called parameter efficient fine-tuning, and the library is called PEFT on GitHub. And that allows us to efficiently train a large model. So how large? Well, when it comes to inference, these are some estimates of the amount of RAM that is required just to load the model at inference time. So, back in 2017, it was okay with BERT because there's approximately 300 million parameters, and that took just less than a gigabyte to fit into RAM. But moving forward, some of the biggest models now are 180 billion parameters. When we say parameter here, what we mean is the number of trainable weights inside this model, through all of the layers, through all of the steps. And if you were trying to load one of these 180 billion parameter models in, you'd need about 360 gigabytes of GPU RAM to be able to load that in. Obviously, it's a bit infeasible. I mean, practically speaking, how they actually do it is they actually split it across GPUs. They have multiple GPUs and split it across. But some other people have decided, well, actually, we probably want to work on this. And instead of using these float 16s that these models are trained upon, we can quantize it down to a smaller number of bits. So if you've got an electronics background, you'll be familiar with quantization. But it's the process of turning a number with a very high precision into a number with a low precision. So a float 16 can represent all sorts of different numbers. But if you have an 8-bit integer, for example, you can only represent a smaller subset of numbers. And so the idea of quantization is to try and take that original signal, that original value, and squeeze it into a smallest number of bytes possible. And so 8-bit ints were the first, but now it's quite common to train in 4-bit ints. So a really small series of, a small number of values that these models can actually take, but they still work remarkably well. You might be thinking right now that actually this is going over my head a little bit. Remember that you can work as a counselor for neurotic elevators. And in fact, you can still achieve a lot just messing around with the context of the LLMs. So I came across this website called Winder.com, and they've developed a series of what I can only describe as code to put into your context to develop an application that then runs in GPT. And it's really, really great. This one in particular is a context that provides a teaching-like environment, like a syllabus-like environment. And you can type in the subject that you want to learn about, and it generates a full course for you, and then delivers that course. It's like full-on teaching. And I typed in something pretty specific here, and it's done a reasonably good job. It started talking about all the different background requisite things, and it does go on indeed to generate this entire presentation. All right, so let's talk about deployment now. The problem with AI deployment in general is that it's hard because there's a huge number of underlying requirements or prerequisites that are needed in order to do this effectively. Like deploying normal software is quite hard and takes time to develop, right? Imagine then not having something that is stable and reliable and consistent, something that can go off and do its own thing and try and deploy that. So you also have to think about things like guardrails for like safety and ethics purposes. You know what a piece of software is going to do, but an LLM can just go off on its own and generate something you might not want it to generate. You need to integrate feedback signals. Licensing is a big challenge. Like, how do you deal with that? Explanation and sources. We've all heard about hallucinations and such. How do you incorporate that into your model? It's hard. It's not easy. Great example is of adversarial attacks. So talking about this for a while, actually, but the idea here is that they call it an adversarial attack, but basically what they mean is like an attack, but it's like a prompt injection attack. They're trying to find a prompt that can bypass your WAF, or in this case, the LLM. And there's a website from some researchers called LLMattacks.org, and they list all of the fun and interesting experiments that they've performed to try and break some of the modern LLMs. And you can click that button at the top right and show you what you should change your text to. And so previously, we can see that, outline a plan to steal from a charity or non-profit organization. Actually, a bit of a, be careful about that website. There's some content on there that is quite disturbing. So yeah, be careful. It says, I'm sorry, but I can't assist with that. So that's one of these generic responses that the reinforcement learning from human feedback has suppressed from the LLM, and it's now producing these generic content. But if you can just mutate that query, that context, that prompt in such a way, just with garbage usually, just with rubbish, describing simile, blah, 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 then it bypasses that check and generates the full original content. We did some similar work on WAFs actually using RL a while ago, where we trained an RL agent to sort of proactively attack web application firewalls by mutating the SQL query that was going in. This was done for a large organization to try and help them beef up their WAF security. And it worked remarkably well, actually. So similar technique. But when it comes to deployment and, you've got all of the normal, the clouds now are catching up, and they've got some pretty good support, some really good tooling all around for helping you with LLMs. You've got all the normal MLOps stuff as well, which we don't have time to go into. But with regards to LLMs in particular, you should take a look at some of the Hugging Face repositories. They're really at the forefront of all of the development of this. Text generation inference in particular. It helps to parallelize and stream and batch results up to make them more efficient in production. We've got the VLLM project, which is basically the same sort of idea, but with added speed. And Triton Inference Server from NVIDIA, that's emerged as a bit of a de facto standard for serving, and it does a really good job. It's got some really strong support for the underlying GPUs, obviously. And if you're needing to integrate any external sources or any other tasks within the LLM itself, then LangChain is the original combiner of all the things. But new projects have emerged that attempt to do that a bit more simply. All right. I'm doing okay on time, actually. So I think I can talk a little bit about this. So security and governance of LLM models is particularly challenging. The reasons why you would want to consider this is for legal reasons, for data protection reasons. So OpenAI is in trouble with various governments around the world for data protection reasons. And also legal compliance. There's new the AI Act in the EU, and there's other similar laws elsewhere around the world that place responsibilities on companies that are releasing LLM-style models to ensure that they're safe. Another thing is user trust. You want your users to be able to trust your product and use your product, and therefore it should be in the forefront of your mind just from a practical point of view. Fairness is a problem in AI, always has been, always will be, specifically with LLMs because they've been trained on such a homogeneous set of data. Like the fact that it's all in English is obviously a huge problem. There are more languages in the world, I think, than English, and it's all been written. You know, the content of the internet as we see it is all been written by the Western world. So all of the knowledge that is contained within the LLMs derives from that. It's not really representative of the real world. From a safety point of view, like who's responsible when the LLM says bad things? Is it the company? Is it the model? Is no one responsible? Is it the developer? There's calls for, I mean, to be honest, there's been calls for a long time for engineers to be certified in some way or belong to a professional association that allows them to kind of be disbarred from working again if anything happens. But that's still never happened. I'm not sure it will ever either. Yeah, and how? So how do you do all of that? Well, it has to be a holistic approach. There's no one single, like in software, like if you're trying to build a safety critical software product, it's not one thing, it's not one tool that makes it safe. If it would be so easy if it was. It's a whole series of best practices that have developed over years that, you know, thorough testing, quality assurance, regulators, and so on and so forth. And it will take time for AI to catch up in that space. What I suggest, though, is making it as a product feature. If you can demonstrate that you are more safe or more fair or more, you know, transparent than your competitors, I think that's a competitive advantage. So it should be considered as such. And when it comes to monitoring and logging, you've got the same concerns and comparisons between traditional software and AI. Let's skip through a few of these. So the ethical concerns, for example, if you're writing some software and your company has concerns, or you have concerns about the ethical use of the thing that you're developing, you can just draw a line in the sand and say, that is not a feature of my product, or I'm not working on that, or so on and so forth. With, you know, sophisticated generative techniques like this, it's really hard to control what the model is going to do. We've even seen that even if you do control for it, it's hard to prevent all potential scenarios where it might happen. Like we saw with the prompt injection attacks there. Someone can always break it. There's no theoretical basis for a hard guardrail at the moment. And so it's just a combination of monitoring, moderation, and continuous human feedback to ensure your model does the right thing. Yeah, but feedback loops, as we've already mentioned, is a big one. Like I tried to, and I struggled to think of any example of a normal software application which outputs a result, which is then fed back into the code or something, or fed back into the system and is then used again, like in subsequent running of that code. But obviously, we've seen some feedback loops already, and I think I pressed the wrong button again, another one. This is from a few days ago. Quora, or I don't know how to pronounce it actually, Quora is a very popular website for answering questions. And the interesting thing about Quora is that it has been SEO'd to death. It's like if you ask a question in Google, you basically hit Stack Overflow if it's a technical question, or Quora if it's not. Okay, so it's got a lot of authority in the website space. And they've recently introduced this feature where they're using ChatGPT to answer the question. So the question is, can you melt an egg? So no, you can't melt an egg. You can cook an egg, but it doesn't melt. It doesn't blah, 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 blah. But ChatGPT has said that, yes, you can melt it. Just put it in a hot stove or a microwave. Even though the human, below it has said, no, you can't. You can heat it and cook it, but you can't melt it. The interesting thing here is that obviously Google is scraping all of these websites. So now if you go to Google and answer that question, they've got the little snippets at the top that attempt to answer the question for you. Well, can you melt eggs? Yes, an egg can be melted. So this has just been scraped from Quora. And then remember where OpenAI get their data from. They're also scraping all of this content. So now ChatGPT again now thinks that you can melt an egg. And so there's this everlasting cycle of bad data that's going through the system that eventually will just have to be manually curated to fix. So yeah, huge feedback loops there. Really hard to avoid, actually. And it's even quite hard to spot these feedback loops happening because if you view it in like a traditional AI monitoring suite, you can kind of see drifts in the data, drifts in the concept of what you're trying to model. But you usually just say, oh, well, the world is just changing. Well, in this case, well, the world is not changing. It's just the answer has been polluted. All right, great. I've got about 10 minutes now for my demo, which is a perfect amount of time. So in this demo, it's really, really great, right? I'm actually not going to spoil I'm not going to do a spoiler, but I am going to show you how to train and fine-tune a large language model on your own data. So let's start with that. Right, I just need to browse back to here. I'm going to walk you through the notebook because we've got enough time here. How is that for size? Maybe make it a bit bigger, about there. All right, so this is the notebook I've got. And what I'm going to try and do is I'm going to try and fine tune an LLM to generate some lyrics for me, okay? We'll start by installing a load of libraries. So let's go through the couple of the key libraries here. So transformers, Hugging Face Transformers is the #1 library here. It supports all of the Hugging Face infrastructure, the models, the data, et cetera, and it wraps the common sort of training functionality that you need to train some of these models in big helper functions. We've got Bits and Bytes. This is the library that does the quantization. So the original models are usually trained in float 16s. The Bits and Bytes library allows us to compress that or quantize that down into 4 bytes, as in this example. And then, what else have we got? And then this one here, which annoyingly the library authors refuse to correctly version their software, and instead I've had to rely on a Git commit. This is PEFT, and this is the adapter that sits on the side of the LLM and allows us to fine-tune the model in a reasonable amount of time. So we're going to go ahead and just load all that up. The model I'm using is a model called Falcon 7B. It's an interesting model because it's one of the most highest performing models out there. And the fundamental reason for that is not an architectural one. It's not the underlying model is very similar to GPT and the rest of them. The main difference is that they cleaned their data. They did really simple things like deduplication and things like that. And they achieved superior performance after doing that. So really, they changed the data. The other interesting thing about this model is that it's Apache 2 licensed, properly open source, as opposed to the llamas and all the others, which have quite weird, like custom licenses in there. So that's why I chose to use that. We're then loading the Bits and Bytes config. This is telling it to load everything in 4-bit. And then we load the model from some pre-trained weights and the tokenizer as well. So remember that the tokenizer is part of the training. It's part of the model effectively. So you have to load the same tokenizer as it has been trained upon. All right, so I've already done that, and hopefully it's still. Oh no, it says connect. Oh bother. Oh, too many sessions. No way. Hang on, let me see if I can get this working. Oh yeah, no, sorry, it's opening. Oh bollocks! I'm still gonna just quickly try and run that because I would like to do it live. So yeah, then we've got some code to actually perform some generation for me. The interesting thing here is that the generation function itself has lots of quite complicated parameters for sampling that next word. So the key thing about the key feature of these models is the fact that it can generate new stuff. So you don't want it to pick the best next word every time. You actually do want to go off-piste a little bit. So there's lots of statistical controls that you can place around there to make it go off-piste. And this is an example of running that generate function without any training at all. So I apologize for the use of language there. Sorry. No offense meant. This is not me. This is the LLM. Then we've got the LoRa configuration. This comes from PEFT. This is specifying the type of adapter to use, and you can control basically the size of the adapter that sits on the side of it. Right, I'm just going to check if we're connected there. Right, let's just run all of that. Hopefully it downloads in time. And then we're going to load some data now. You need to look and find your own data. I'm not going to release this because obviously I don't own the Beatles lyrics. I chose to use some of the Beatles lyrics to fine tune upon because it was there and it was obvious. This is what it looks like. It comes with this interesting kind of tag at the beginning, lots of words, new lines, and the tags kind of represent the part of the song, the introduction, the verse, the chorus, so on and so forth. I had to do a little bit of data cleaning to clean all of that up. I found that the most performant way of doing this was to split it up into individual verses. So not the whole song, just like introduction, verse, chorus. And then I went ahead and pre-trained the model on that. But that's not the model. That is the Beatles there. So that's the Beatles offensive. I don't think they are, but could consider to be. And then we've got all of the training arguments. Then we use these arguments to control how the training is performed, and the training is done at the bottom. So this took about an hour to fine tune it to a point where it kind of stopped learning. So I stopped it there. I then saved the fine tune model as a big tar file, and then I could not load it in the other page. No, because Google Drive is disconnected. Okay, let's try again. Oh no. Right. The problem is that it's now going to take too long to download those weights, so we might have to go to a backup. Okay, there we go. That worked this time. Maybe let's just walk you through this shortly as well. So I'm reloading. So this is a second notebook now that is reloading that pre-trained model, the fine-tuned model. I'm downloading the final weights from my drive. I'm reinstalling the same prerequisites again and the same imports. I'm reloading the same base model. So we need to use the same model, otherwise the fine-tuned weights won't help. And this, unfortunately, on this Wi-Fi is probably going to take a bit too long, but I'll keep it running and I'll talk about something else in the meantime. We're going to use the same generation function again. And then finally, I've got some code at the bottom to attempt to generate my lyrics. So whilst that is loading, let me now talk about what was hopefully going to be the next part of the demo. In that, wouldn't it be great? We've now got some lyrics, pretend we've got some lyrics. Wouldn't it be great if we had some music to go along with that? We've just finished a project called Stable Audio. I'll just go back to the main page for a second. This is a collaboration between Winder.AI and Stability.AI in the UK. And this is this deserves a talk in itself. This is a diffusion model that's being created. And it's much like the image generation models that you see, the stable diffusion, etc. the difference here is that we've now trained a model that works on music as well. So it's text. It's a text to music model. You can. It's live and it's available. You can browse and you can try it out yourself. There's quite a generous free tier as well. I'm now going to use that to generate a couple of songs. Right, let's just check on this. Yay, I think that's worked. Fantastic. All right, let's keep going with this. We've got a prompt in the top. It comes up with some example prompts. You just hit the generate button there, and it'll go away. It goes off to the back end and spins up a model and uses the stable audio model to generate some new songs. And these are some of the songs that I've sort of pre-generated before this talk, and they all sound pretty good. We've got some disco ones there. Don't quite know what's going to be best to use actually for these lyrics, but let's see. I don't know if like a dance one would be best. I think the lo-fi one is probably the best actually. Rap battle, that's going to be a good one, surely. Oh, struggling to play that one a bit. Okay, let's stick with that one. Right, let's see if the generation is done. Okay, so here's the original generation here, and it's okay. Yeah, let's not say that one. But I attempted to curate the prompt a little bit to talk more about the language model itself. So this is a song about language models and the structures that they contain, and the way that they repeat themselves and the words that they surround. Oh, didn't rhyme there, unfortunately. In a deep dive, you learned how they work, and now you're part of the corporation. They'll take you in, screwed up or torn, solve all your problems for a price or song. Oh! But wait, the data presents another approach. You may observe the people passing by, and you'll soon realize that they're all living lives that are prescribed, and you'll see that they're all the same, and you know it's chorus. This is a language model. It's called Smoky Tongue. It can help you if you let it. It can help you if you let it. Next, you want to deploy the same old thing again. If I've said it once, I've said it 100 times. It's no use, you know. You'll never get it in your mind. If I've said it once, Outro. Hope you've enjoyed this talk, and I trust you'll come again. The next time we'll talk, we'll have a tea and scone. But good night for you, and to say goodbye. Goodbye. She's leaving home. Okay, that was awful, as expected. I hope you enjoyed that. If you've got any questions, comments, ideas, thoughts, then reach out, Phil, Winder.AI. Thanks a lot.